So the last class we talked about how there's a couple of different ways of looking at probability, and we're beginning this class discussing the basics of probability. The reasons why we do this is for multiple reasons. One, probability just by itself is an important thing to know as far as trying to assign some sort of quote-unquote likelihood to whether or not events are going to happen. Another thing is that when we talk about random variables and probability distributions, then this is an extension of probability. It takes a probability space and then it adds another component to it. So it's important to understand how probability works, and yeah, today we'll probably get some into random variables, and next week there's some other parts about probability that I would like to continue to talk about. But so far, as far as the way that I think it's the approach that I'm taking when I'm talking about probability is this one, that probability starts with a probability space. This is two things. It's a set of all possible outcomes. Each of these outcomes are called elementary events, and these can be anything you want. Along with the set of events, you have a function that maps each of these events to some number between 0 and 1, such that all numbers add to 1. That is what makes a probability space. It's important to remember that a probability space describes exactly one realization of an experiment. So, for example, if I take this set of heads and tails, this is part of a probability space that defines flipping one coin one time. If I'm interested in flipping the same coin 2 times, then I have to define a new probability phase, or a new probability space, like we did here. Actually, okay. So this idea of a joint probability space is a lot of the time the actual types of probability spaces you'll be working with. And a joint probability space is when you take different spaces and sort of add them together to create a mega space. And in this mega space, this can capture, for example, doing things in sequence through time, or having lots of different events all occurring together. And what you're interested in is some subset or some realization of this combination of events. This is a joint probability space. To create a joint probability space, you're following a definition. So you just sort of plug things in. You don't have to worry too much about the being creative or anything. It's just a process. So the process involves creating the set and the function. The set is just a set product of all of the sets that define the smaller subspaces. And the function is just the algebraic product of all of these events occurring. So here's a concrete example where we have, we want to flip either one coin, the same coin 2 times, or we have 2 coins, and we flip each of them 1 time. It doesn't matter, they define the same set of outcomes, and we end up with this space. So we have our set, and we have the probability function. All right. There's also a notion of independence, where there's 2 equivalent definitions. One which is based on conditional probability. This says, in effect, that if you have 2 events A and B, if having knowledge of B doesn't change the probability of A, then A and B are independent. The second one says that if the area of A and B, their intersection, A intersect B, is equal to the area of A times the area of B, then they're independent. Okay, so these are the 2 definitions of independence. You can use whichever one you like, but in many cases, you're only going to be able to use one, because it depends on how much you know about the conditional probabilities or the individual ones. Okay, so we gave an example of this before. And then we talked about conditional probability. So conditional probability is when you are given knowledge about something happening, and because you now have this knowledge, you can work with a new probability space. So originally here in gray, this might be your original world of area 1. And if I tell you that B occurred, then you can make B become the new world, and everything in gray can sort of fade away, and then you adjust all of the probabilities to make sure that B is itself a probability space. And we left off on Bayes' theorem, which is just this equation. And this was the first thing that we saw that wasn't just a definition. This is a theorem. So this is something that we can derive. A derivation is also sometimes just called a proof. So it's a true statement that you can demonstrate using definitions and axioms and other theorems that you've proved before. But because it's our first theorem, we can't use other theorems. We just use this one. Yeah, and we ended class talking about why or how this Bayesian way of thinking has itself become an entire way of thinking about probability. So you can imagine probability as conducting an experiment some very large number of times, and then you just count the frequencies of events. And the frequencies is going to be some number between 0 and 1, and that's basically the probability function, the mapping function of events to numbers. It's their frequency over some large number of experiments. In the Bayesian, from the Bayesian perspective, it's that you have some prior belief about something. The first part of this is called the prior. And then this is called the likelihood. So the likelihood of your data, or the likelihood of the data given your hypothesis, and you divide that by the probability of the data, and you get the so-called posterior probability. This is what your new updated belief is. Fine. I would like to, first I'm going to ask if there's any questions about that after a quick review, and if not, then I have a couple of examples that I would like to try to go over with you. No questions, okay? All right, then let me think of, I'll do this on a different, just practice examples. Okay, there was a radio show that I used to listen to called Loveline that was on in the 90s. And the two hosts would play a game because they got bored on the radio. Let me increase this. Okay. Imagine a game where two friends are listening to the radio. Let's say in California. There are many different Spanish-speaking or Spanish music stations. And the game is to bet how long is to, after turning to a random Spanish music radio station. How long until ranchero music starts? It is okay. So in Spanish or Mexican music, there's lots of typical instruments that they use: guitars and dulcimers and drums and stuff like this. One of them is horns. So like a trumpet, for example. And so they would play a game where they would try to turn to a random radio station, a random Spanish music radio station, and they'd bet how long it took for the horns to start. It could be 0 seconds, like you turn to it and immediately there's horns. It could be 5 seconds, 10 seconds, whatever. Let's say that the probability of hearing a horn in the first 5 seconds is 30%. All right. So this is the question. First of all, I want to make sure that you guys understand the setup. Do you understand the rules of this game? Yep, great. All right, then I would like to give you let's say 5 minutes to try to solve this yourself. Share this. Great. Okay, and when I say to solve this, what I mean is that I want you to put together a probability space. So that includes a set and a function, and use that to come up with whatever the probability of winning 3 games if you bet 2 out of 3 times that there will be horns in 5 seconds or less. All right. So I don't just want a number. I want a probability space that gave you that number. Okay, so I'll give you 5 minutes. Everybody can see this clock, I'm assuming. So yeah, grab a sheet of paper, a pencil, whatever, and I'll come back after you guys have a little bit of time to actually work through some stuff. All right. Okay. Anybody think that they have an answer? Nope. Okay. .063. Okay. I think at least no. Okay. Anybody agree with Raymond? Or have a different answer? No. Okay. Then let me ask. Let me pause this.
70%. So then the probability.
Very good. Hang on just a second. I'm going to write some of this down. So I'll do this game. You said that there's either horn or no horn. And this is, I don't know, game. Sure. Okay. Horn, no horn. And then?
And then I did like probability of a horn being 0.30.
0.3. Yeah. Okay.
Yeah.
Okay.
That's what I mean, yeah.
And
And
so.
then
Mhm.
and then probability of no horn being 0.7.
All right.
And then like after that, I just thought like if you're looking for, 2 out of 3 times for there to be horns, you just do zero point 0.3 times zero point 0.3 times zero point 0.7, because out of those 3 times it doesn't horn.
Okay. And this is 0.063. Okay, so because 2 times you heard a horn, hey, 1 time you didn't, and so that works out to be this number. All right. So this is not quite right, but it's a very, very, very good start. Especially this part. So I'll get rid of this and I'll explain. So the probability is a little bit higher than this, and the reason why is because you just need to. This would be correct if the first time there's a horn, the second time there's a horn, and then the third time there's no horn. But this just says that any 2 out of the 3 times there's horns. So really it's 3 times this probability, because the this is another sort of possible outcome, and this is another possible outcome. And so the probability is actually 3 times higher, because the no horn could be the first song or the first round of the game, the second round of the game, or the third round of the game, so long the other 2 have a horn. So that's a very good start, but this thing is coming from where? I mean, these 3 numbers that you're multiplying by each other. First of all, I hope it makes. Raymond, does it make sense why the probability is higher than you estimated?
I'm a little bit confused. So wait, each game they do it 3 times?
No, no, no. They play the game 3 times. What's the probability of winning all games if you bet that 2 out of 3 times there will be horns?
So like,
So,
is each game they're flipping through the station 3 times?
yeah, so we're going to play the game. We're going to play this 3 times. So, radio off, go to a station, and let's do this last possibility. This one. If I turn on the radio and within 5 seconds there's no horns, and then we change station, and then there's horns, and then we change stations, and then there's horns.
That's one game. Okay.
Well, that's the same game being played 3 times.
Okay.
And so if your strategy, or if you sort of win the bet, if 2 out of the 3 are horns, then this is 2 out of 3. I mean, it wasn't horns the first time, but it was horns the second and the third time. So that's still 2 out of 3. Like, you should still win the. This is sort of a, I don't know, a 2-layered game, I guess. There's the base game.
Oh, I think I
and then
kind of see. It's like they're all in different orders, right?
Right.
Okay.
Yeah, just different orders. Exactly.
All right. Yeah, that makes sense now.
Okay. But there's still a big gap between this probability space and these numbers. So this is what we'll be going up to. And in case anybody cares, this is 0.189. Okay. Thank you very much, Raymond. How about I don't know. Baha. Do you have a mic?
Hey, I have a question before you get to Baja.
Great. Yes.
So why I got lost with the elementary events is because like you were giving the example of the die before. You said like if you had to like roll it twice, for example, you would have to multiply like head tails by each other. You would have to like make a new omega with the joint like 2 rolls.
Yes.
I thought it was the same scenario with this since we're playing the game 3 times.
Very good. Let's stay with you, Brian. That's exactly where I was going. And by the way, Jake, you don't understand the question. It's asking the probability of winning all games, but you only bet for 2 out of 3. You win. So again, this is sort of 2 levels of games, right? If you play roulette, maybe like you go to Vegas and you play roulette, then you could bet on any individual game of roulette, but maybe before you play, you make another bet with one of your friends that I'm going to win exactly 2 out of the 3 times of roulette. And so you and your friend sort of have this side game where it involves you going and playing another game 3 times. So you could win whatever money you get from the table or from the roulette game. But if you win exactly 2 out of 3 times at the roulette game, then you get some extra money from your friend. Hopefully that makes sense. If it doesn't, Jake, remind me and got it. Great. All right. So, Brian, what you said is exactly correct. So this is playing the game exactly 1 time. But this is the wrong probability space. So let's just start with the space part. So there's 3 rounds of the game. I'll call it this game cubed because we're playing it 3 times. So what is one example of an event here? Brian.
One example would just be like horn, no horn.
Horn, no horn. I'm gonna shorten this. Horn, no horn. That is 2 times. We're playing 3 though.
So could it also be horn, horn, no horn, no horn?
That's 4 times. Horn, horn, no horn, no horn. This would be an example of if we played the game 4 times, but we're playing the game 3 times. You're almost there. Just split the difference.
So just take away the last no horn.
Perfect. All right. So this is one possible outcome. So we're playing the game 3 times, and there could be horn, horn, no horn. This happens to be a case where you would win. Okay. What's another event? What's another possibility?
Horn, no horn, horn.
Horn, no horn. Excuse me. Okay. Before I write them all out, do you know how many of these events there would be?
9? I don't know.
9. 8. 8, actually. So this is, think, because it's like flipping a coin, right? I mean, horn or no horn, you're flipping a coin. If you flip a coin 3 times, then how many possible outcomes are there? I mean, there's 2 outcomes, heads, tails, for the first. There's 2 outcomes, heads or tails, for the second. So if you flip a coin 2 times, that's 4 different outcomes, right? Heads, 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 tails, tails, heads, tails, tails. But if you flip it a 3rd time, then now it's 2 cubed, which is 8. So this is heads, 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 tails, heads, tails, heads, tails, heads, heads, tails, tails, heads, tails, heads, tails, whatever. We can write them all out. In fact, we might as well. And this is another way that you can think about constructing it, is this is a joint probability space. So this sigma of the game, this is playing the game 1 time, but we're doing it 3 times. So you can build the set like this. Let's see. I guess I'll stick with you, Brian. Can you help me finish these 8 possibilities?
Sure. No horn, horn, horn.
Okay.
Let's see. No, you know what? I think I'll pass the torch on to someone else.
No, it's okay. Hang on. So like there's a pattern here, sort of. That's good. This is when there's no horn 1 time.
Mm-hmm.
There could be the no horn on the last time, the second time, or the first time.
All right.
Okay, so stick with that same pattern, except now let's say that there's only 1 horn.
Okay. So head, no horn, no horn.
Yeah, horn, no horn, no horn. Okay.
But aren't we doing the probability of winning like having the horn go off 2 times and not going off?
Yeah, so that's an event that we care about. But right now we're
Oh,
building
this
the
is all the
space.
events, right? Okay,
Yeah,
okay.
these are all of the elementary events, and then there's one event that is going to be some subset of these.
Okay.
Namely, the ones that you've already mentioned. These are the ones that are going to define the event that you win. This winning all games. If you were to bet exactly 2 out of 3 times, there will be horns.
Okay. No horn, horn, no horn.
Yep.
Horn, no horn, no horn.
I think you mean no horn, no horn, horn.
Yeah, no horn, horn.
Okay. And then there's 2 more.
Horn, horn, horn.
Very good. And
No horn, no horn, no horn.
very good. So Brian, do you understand why you were right. You had the good a good intuition that you need to somehow construct a bigger space like we did with the coin. Does it now make sense to you why you need all 8 of these events?
Yeah, no, that makes sense. Yeah, I just went about it the wrong way initially, but
Okay,
that makes
good. Yeah, that's why we practice. Cool. All right, thank you, Brian. How about Kevin? Do you have a mic? So what I'm interested in is now the probability of these events.
The probability of the horn, which is probability of one, the numbers probability.
Yeah. For example, the probability of horn, horn, no horn. What is this equal to?
It was the 0.6 or whatever.
0.62.
0.62 or 0.63.
Well, why 0.6? Don't give me the final answer. Just give me each piece of it. So, for example, instead of saying the number 8, say 2 times 2 times 2.
Oh, okay. So it was just 125. I'm not exactly sure.
Okay. Let's see. Let me go back here really quick. So we are in a probability space, a joint probability space. What we've just done is we've constructed this, and now we're trying to construct these, the probabilities. And so, for example, this one event, or the event rather, yeah, this event here, where you take the first element from the first set, the first element from the second set, and all the way down to the first element of the last set. That event is just multiplying each of these individual probabilities. In fact, here, just to give you a hint, further than that. It's one of these down here at the bottom. A, B, C. Any guesses on which one it would be of these? A. All right, why A?
Because the horn is 3, and then no horn is 0.7.
Very good. Okay. Thank you. All right. Thanks, Kevin. So, yeah. So that's the probability of the first event. And actually, this will be the same for the probability of horn, no horn, horn, and the probability of no horn, horn, horn. There we go. Why are all of these the same? Because this algebra doesn't, I mean, each one of these is the same number, whatever it is. Whatever, all of these are equal, and these are equal, and those are equal. So the probability of each of these first three events are the same. All right. How about Kyle? You have Mike?
Yes.
Great.
Yeah.
So we have the probability for the first three of these events. How about the probability for the rest of them?
So that would be 1 second.
Mhm.
0.147. That would be for sorry.
Yeah, so give it to me in like this form, like something times something times something, instead of whatever the
Okay,
result is.
so for the probability of the horn, no horn, no horn, I would
Yep.
do 0.3 times 0.7 times 0.7.
Very good. What was the number that you said? What does this equal?
I did the horn, no horn, no horn.
Yeah, and so what was the number? It's 0. What?
Sorry, 0.147.
147. Okay, great. So yeah. For the purposes of this type of question, I prefer things in this way. Because
Okay.
0.147 could be a lot of things. It could be 0.148 minus 0.001. It could be 1 minus 8.53. But this 0.147 is not any of those. It's this. It's 0.3 times 0.7 times 0.7. So this is a sort of special 0.147 because it's actually this. All right. Sorry. Okay. Fine. All right. And okay, so for the rest?
Like for each of them? Oh wait, there would be. Oh, and there's also the one that's the 3 horns, which would be the.
Well, hold on. We haven't
0.3 times.
we haven't gotten this one yet, or this one. Let's just stick in
Okay.
order.
Well, aren't those the same numbers? It would just be 0.7 times 0.3 times 0.7.
Very good. All right. Yep. Okay. And now you say for horn, horn, horn.
That would be 0.3 times 0.3 times 0.3.
All right, and the last one? The probability of no horn, no horn, no horn?
Okay, and that's 0.7 times 0.7 times 0.7.
All right. Very good. Okay, thank you, Kyle. So, all that we've done so far is build our probability space. All right, this is why I was giving you guys like 5 minutes to work through it. Yeah. People are inclined somehow to take this and then just sort of jump to did I erase it? To jump to these kinds of numbers, whatever. You define, or people will define this sort of base game, and then they'll start giving these kinds of numbers. But this numbers, like that's not a part of this game. This game has 0, 1, 0.3, or 0.7. That's it. Again, it's one realization of the experiment. So if you want to play the game 3 times, you can. You just have to build a new probability space. So for the purposes of this game, they play the game 3 times. This describes all of the different outcomes of playing the game 3 times. There are no more. There's exactly 8. I hope it's clear why there's 8. If you think that there's 9, still try to think of the 9th and let me know if you come up with it. But now we have our set of events and the probabilities of any of these events. And keep in mind now, each of these is one event. This is one event playing a game 3 times. It's the realization of the experiment being done once. So each of the outcomes have 3 components, but it's still one outcome. There's 8 outcomes of playing the game 3 times. So, actually, let me do this. Mega game cubed. So this is the whole outcome. All right. Let's see. So how about a nary?
Yeah.
Hey. So I already wrote it before, but I apparently erased it. So what's the probability of this? And where
So
does it come? Yeah.
that is 0.3 times 0.3 times 0.7 plus 0.3 times 0.7 times 0.3 and then plus 0.7 times 0.3.
Yeah. Why do we need all 3 of these? And why are we adding these together? Why do these get added together, but these here, they got multiplied? Like, why do we add here, but we multiply here?
I'd say because those are all the events where we get horn, horn, no horn, or like horn 2 out of the 3 times.
Yeah, so why do you add them together? I mean, why not multiplying or subtracting or something else?
Because that's the how many times that we are playing the game, like 3 times. So
Yeah, you're playing the game 3 times, but here, we're multiplying 3 numbers together. Here, we're adding 3 things together. So why are these multiplied and these are added together?
Would you multiply when they're like all together, but like you add when they're like separate from one another?
You're getting close, yeah. So when you say they're separate from one another, what do you mean by that?
Like,
they're independent.
yeah.
These are independent, yes, and that's yeah, that's part of it. Did I talk about disjoint events the last time? Maybe not. Okay. Well, I know that I did talk about viewing this as a probability space. This is omega game. Game cubed. And here we have horn, 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 no horn. Whatever. No horn, no horn, no horn. So there's 8 of these altogether. And these are each of these are disjoint. And so the probabilities that we care about are, let's say, this probability and this probability and this probability. And so you add them together because what you care about is this whole chunk of the horns. Let me write. Let's see. Horn, no horn, horn. No horn, horn, horn. Right. So you add these together because they're disjoint. Oh, I'm sorry. In fact, these are not independent. These are not independent. I'll touch on that in a minute. But these are 3 separate events, and then here's okay. So the probability of an event is the sum of the probabilities that comprise it. I think that was, let me go back here. Here. The probability of an event is the sum of the probabilities of the elementary events that define it. This was our definition of an event. So here, the event here is comprised of 1, 2, 3 things. And so the probability of this event is the probability of each of the things that comprise it. So it's the probability of this first one, horn, horn, no horn, plus the probability of the second one, horn, no horn, horn, plus the probability of this third one, no horn, horn, horn. Why are these multiplied? This is because this is a joint probability space. And that is the part of the definition of a joint probability space. Here. So the probability of an event here is the product of the events that comprise this is an elementary event, right? Here, maybe I should emphasize that. Here. This is an elementary event. What I mean by an elementary event, just to remind you, is these things. There's 8 in this space. There's 8 possible outcomes. Each of these outcomes you can call an elementary event because they get no smaller. Separate than that, you can define lots of different kinds of events. For example, here, these 3 events we can say are hearing horns exactly 2 out of 3 times. So the probability for the elementary events of a joint probability space is the product of each of the individual events that comprise it. So here, this is 0.3 because that's this first heads. This is 0.3 because that's the second heads. This is 0.7 because it's this one. And I also said before that when you're talking about ands, that corresponds to multiplication. So this is hearing a horn on the first game, and hearing a horn on the second game, and not hearing a horn on the third game. So all of these get multiplied. Whereas here, this is an or. So the way that you can win this, win the bigger game, is if you hear 2 horns on the first 2 times, or you hear a horn on the first and the third times, or you hear the horn on the last 2 times. And so for ors, you add them. For ands, you multiply them. Whatever. There's multiple different ways that you can think about this. I'm trying to give multiple different ways. You can latch on to whichever one you like. If you have one that you like and I say another that confuses you, you can forget about it or ask. Okay. Very good. So, by the way, on your homeworks, this is the type of question that I would give you. Same thing on an exam. This would be, I think, like a fair homework or exam question. Is there any way we can know the number of HHNH without listing all elementary events? Yes, there is. Yes, there is. And we'll get to that when we get to counting. Sure. Yeah, I can post the reference notes, sure. Instead of posting the OneNote document, if you have OneNote and you want access to this, give me whatever your Microsoft address is, if that's okay. That way I can just, here, there's a class notebook. I can add and remove students. That way you'll just have access to it, and I don't have to export it and upload it every time. It's just because I'm lazy. So if that's okay with you. Or if I don't know, if you don't want to do that, I can put it up. But yeah, for anybody with OneNote, I can do that.
Okay, I have no idea what my Microsoft account is. I don't think it's like my student one, so
okay,
like my
sure.
student email.
Sure, no problem. Okay, yeah, I'll just post the whole notebook. So what I'll do for that is for that I'll delete after every class. I'll delete the OneNote file, and then I'll just re-upload a new one. And the new one will have this entire whatever, this entire notebook together.
Yep.
Yeah, yeah.
Okay,
Um,
thanks.
Yeah, that way there's not like multiple versions and stuff. It'll just be one. Great. Yeah, so to quickly answer this question, and we'll get to this maybe probably next week, I guess, because I want to jump ahead and get to random variables sometime today. And then I'm going to be passing over some probability stuff, but this would be a combination. Combination. So this is actually an example of a binomial distribution where n is the number of trials, k is the number of successes, and p is the probability of success for one trial. So here, n equals 3, k equals 2, because we want to hear the horns exactly 2 times, and the probability of a success that is hearing horns is 0.3. And so this has an equation that is n choose k times p to the k 1 minus p to the n minus k. Whatever. So that's the shortcut. And you can count them. So this is exactly up here. Let me get these both on the same screen. Perfect. So this p to the k, here, there's 2 of them. And then the 1 minus p, that's the 0.7, to the n minus k. So that's the rest. You're playing it n times. So, you know, if you have n here and you split this k, this is k, then this is n minus k. And so k plus n minus k equals n. Whatever. So that's this part here. And that's for just one of these. N choose k, this will actually get you the number 3. So 3 choose 2, 3 choose 2 is equal to 3. So this is the fast way of doing it. But it's all of this whole binomial distribution stuff, it's all coming from this. This is what's underlying it. So I know that this is tedious and it's a lot to like write down, but I think that it's important to have a firm understanding of exactly what it is you're doing. Too many people are just presented with this kind of thing on like a sheet, and they try to look for which equation to use, and they plug in the numbers, and what is this actually doing? And they don't know. And so what I'm trying to do is to let you know actually the math behind it. So we're doing the really boring, tedious stuff first. And that way later, when we learn the shortcuts, then you'll know actually what these equations mean. I think that's very important to know where things come from and not just use them because you're guessing. It's yeah. Okay, this is already pretty late. Let's go ahead and take a we'll come back at 7:30. 13-minute break. Yeah. If you have more questions about this, let me know after the break. Thanks. Okay, welcome back, everybody. So, okay. I was asked, can I explain how I get 3 choose 2? So I was going to save this until next week, but because I was asked, I might as well get to it today. Counting. What I'll do is explain the different types of counting and maybe save more examples for next week. That way today I can cover more new material. But, okay, so counting. Essentially, well, there's many different types of counting. For this course and for things probability, namely, there's 3 types of counting that matter. Counting the how would I phrase this? I don't like this phrasing. I'll come up with something better. But really? Can I change this? Do it that way. Fine. In short, for n say here. That's a bit better. Counting the total number of pairings. So, given sets A, B, ... and whatever. No, I'll do it this way. No, I don't want to use that either. S1, S2, up to Sn. This is basically S1, the size of S1 times the size of S2 times the size of S3 times ... times the size of Sn. And each of these are algebraic multiplication. All right, so this would be, for example, Saddam. Example, flip a coin 5 times. Then SI is equal to heads, tails. For I between 1 and 5. So this implies 2 to the 5th. Okay, so 2 times 2 times 2 times 2, which is 2 to the 5th. 2 times 2 times 2 times 2 times 2 equals 2 to the 5th. All right, so this is one type of counting. You flip a coin 5 times. How many different possible outcomes are there if you flip a coin 5 times? Well, you can get heads, 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 heads. You can get, heads, 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 tails, and you can list them all out. You'll get this number, 2 to the 5th. Let me write that cleaner. Okay. Then there's counting the number of possibilities when order matters. This is called a permutation.
So, quick question: the 2 to the 5th, is that basically saying that's how much? Like 2 to the 5th is how many possible outcomes there are for flipping a coin 5 times?
Correct.
Gotcha. Okay.
Yeah, because you have 2 possibilities for the first coin, 2 possibilities for the second coin, 2 possibilities for the third, the fourth, and the 5th. So this could be heads, tails, this could be heads, tails, and whatever. That's why it's 2 to the 5th. Here, this is a little bit more general because, for example, if you flip a coin, then roll a die, then take a card from a standard deck. So, for example, one possibility here could be heads, the 3, and I don't know, the ace of hearts. Right? This would be one possible thing in the set, and the question might be how many things are there in this set. So that would be 2 times 6 times 52. This 2 is the size of the set for flipping a coin times the size of the set for rolling a die times the size of the set for a standard deck. Same reasoning is here. So this is the type of thing that you do when you're creating a joint probability space. And you want to know how many elementary events are there in the space. You can use this first one. And yeah, I like this. Counting the total number of pairings. So I think that's a good way to phrase it. The second is counting the number of possibilities when order matters. So with let's see. Called a permutation. Given n things, there are n times n minus 1 times n minus 2 times ... times 2 times 1 equals n factorial. This is read n factorial. This exclamation point means that you start at that number and then you multiply times the next number down times the next number down, and you keep doing that until you reach 1, and then you stop. So here, an example would be let's see. Eating let's see. The order of eating 3 things off a plate. So here you have 3 choices for the first thing that you're going to eat. And once that's gone, now you're going to eat the second thing. And so this is 6. So for example, if you have an apple, a banana, and a mango, how many different ways could you eat those in a different order? You could eat the apple first, you could eat the mango first, or you could eat the apple first, the mango second, and the yeah, so this is also counting without replacement. So the order of eating, I'll just make it concrete. Apple, orange, mango. Right, so here there's apple, orange, mango. There's apple, mango, orange. There's mango, orange, apple, mango, apple, orange, and orange, mango, apple, orange, apple, mango. And that's it. 6. Okay. So here you're counting without replacement. This would also be if you have a bag with a bunch of balls inside of it, and you want to know, like the, well, whatever. If you have a bag with 10 balls in it, and then you want to know if you take, and each of these balls have a number on them, 1 through 10. And one at a time, you're going to take a ball out, put it on the table, and then take the next ball out and put it on the table, and take the next ball out and put it on the table, and you're never putting balls back in the bag. Then how many different permutations are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 10, 9. 1, 2, 3, 4. You can count them like this, but whatever. Okay, so that's called a permutation when order doesn't matter. And so this is counting the replacement. This is called a combination. Given n things and choosing k of them, this is written n choose k, and this is equal to n factorial over k factorial n minus k factorial. Where does this come from? So let's take the same example of fruits. Example. Have an apple, an orange, and a mango. Choose one to eat. Well, no, I'll do this. I'll say, sure, whatever. Choose one. Then we'll choose two. Then we'll choose three. By the way, n choose 0 is 1. Just by convention. How many ways can you not choose anything? There's one way. All right. That's a special case. Fine. So if you have an apple, an orange, and a mango, and you're choosing one to eat, then you have three possibilities. You can eat the apple, or you can eat the orange, or you can eat the mango. But let's first say that I'm going to think about this like a permutation. So I could eat the n factorial here is apple, orange, mango. How to say? Yeah, no matter what, you start out by saying, okay, well, let me see how many different ways there would be for me to eat all three of them. So that's the permutation. But if you do this, you're going to, let's see. This would be the number of combinations or the number of permutations if you eat all three, but you're only eating two. So this is 2 times 1. That is to say that there's 2 ways of not choosing the 2 things you're not going to eat. And actually, it should be the other way around. Well, it's the same thing, actually. Yeah, whatever. So the n minus k, yeah. There's 2 ways of choosing things that you're not going to eat. And then here, there's 1 remaining way for you to choose the only remaining thing. So this is, you can think about this stuff on the bottom as being a corrective term. First, you list out all of the different permutations, the n factorial, but now you've overcounted. This doesn't show the overcounting as clearly as the second thing does, but you first count all of the permutations of the ways of how taking everything together would be. Then you divide it by the number of ways that you don't choose something, and then you also figure out the number of ways that you could choose something. And this might be more clear when we do the next one here. So, let me copy this. Choose 2 to eat. Okay. So the same thing, 3 times 2 times 1. Now, if you... Actually, here. I'm going to go about this a little bit of a different way. Yeah, we have an apple, an orange, and a mango. You choose 2 to eat. So, let's say that you have, let's see, options. There's an orange, there's an apple, and there's a mango. Okay, 1, 2, 3 things. For the choice, you have 2 slots. Okay, so you could say, well, actually, I'll make this a little bit more complicated. Apple, orange, mango, banana. All right. So you have 4 of these fruits on the table, and you're going to take 2 of them and put them on your plate. Well, you could choose, for the first thing, you have 4 choices of what to choose. The second thing, you have 3 left, three other choices for the remaining thing. So you remove one of them, and now you have 3 left. And so then you choose out of those 3, one of them. The problem is this has overcounted. But this has overcounted. That is to say that orange apple is the same as apple orange. Right? Order does not matter. I don't care if you picked up the orange first and the apple second, or if you picked up the apple first and the orange second. So you've overcounted. By how much have you overcounted? Well, by 2, because that's how many things you're choosing. So for all of these pairs, out of all of the 4 factorial different combinations, I'm not going to write them out, there's 16 of them. Is that right? No, there's 24 of them. Yeah. So out of all of the 4 factorial different possibilities, orange apple is going to match with apple orange, and mango banana is going to match up with banana orange or banana mango, and on and on. It'll be you'll have overcounted by 2 times, so you need to divide by k factorial to correct for this. Correction term is dividing by k factorial. Okay, another way to think about this is why do you divide by k factorial? Well, you've overcounted, so you need to either subtract or divide. Here, because of the symmetricalness, you're going to end up dividing. Now, once you've picked these things, like let's say apple, banana, then you can now rearrange them. Now that you have 2 things on your plate, how many different ways, can you arrange those 2 things? There's 2 ways. If you have 100 foods and you pick up 4, you go to a buffet and it has 100 different food items and you can pick 4 things on your plate. Well, then how many different ways, once you have the 4 things on your plate, could you rearrange them? Because that's going to be your correction term. And given that you have 4 things on your plate, then there's 4 factorial different ways of arranging it. In this example, it would be 4 times 3 over 2 times 1 would be the answer, which is 6. But another way to write this is 4 times 3 times 2 times 1, and I'm keeping this in the denominator. But now there's an extra 2, 1 on top. So I'll put an extra 2, 1 on the bottom, that way these things cancel out. So this is what I mean by the number of ways of not choosing something. And this is more of an algebraic kind of proof that, I don't know, it's not a proof really. But in any case, this is the total number of orderings of all of the things. And then that's going to overcount. So you have to consider this n minus k is just to make things easier. It's so that you can type n factorial on top. If I add this n minus k, then I can write n factorial on top, and it's fine because I'm just canceling out this extra part. This part, the 2 times 1, that's coming from the correction term that you've overcounted. So that's what this k factorial is. Oh boy. Yeah. Sorry, I don't know how much that makes sense, especially the combination thing. It'll make more sense when we work through more examples. We'll get more into this next week. But there was this question about why do we get 3 choose 2? So out of these 3 ways of counting the total number of pairings, counting the number of possibilities when order matters, or counting the number of possibilities when order doesn't matter. Here, I just say that you win exactly 2 out of 3 times. So here, I don't care what the order is. You can win any 2 times. They could be the first 2 songs, it could be the last 2 songs, it could be the first and the third song. The order doesn't matter. I don't care. So out of this set, this 3 choose 2 is because I'm playing the game 3 times. Well, actually, no, it's different than that. It's that I have 3 things. I have horns, horns, and no horns. All right, I have this set. And so from this set, I'm going to pull things out of this set in some order. Right, so maybe this is H, N, H, H. Okay, this is a set. I'm writing it with a set notation. This is not equal to heads, heads, no heads, with parentheses. This is the realization of one experiment. So, and this is a set of things that I'm choosing from. Things that I have 3 things here, and now I'm going to be this is my bag with 3 balls in it. And now I'm going to be pulling out the balls from the bags. So, yeah, I could pull out this one, or this one. But that's the same as if I pull out no heads, heads, heads. If I do this. So these, I'm considering them the same. So this is why you do 3 choose 2. I have 3 positions. And I'm choosing 2 of the 3 to place the horns. Raymond, does this explain your question? I know I'm going kind of quickly, but like I said, I'm sort of jumping ahead of myself. I wasn't planning on getting into counting until next week. You understand now? Great. Okay. So this is, we'll talk more about the binomial distribution next week as well. And actually, this illustrates well why counting is something important in probability, and in lots of things, but especially in probability, because you can count how big this set is going to be before you even construct it, using this all pairings. Yeah. In any case, there's these 3 types of counting. Either you're going to be multiplying all of the numbers together, and it doesn't have to be all the same numbers. Again, with the rolling a die, flipping a coin, and picking a card from a standard deck. You just multiply all those numbers by each other. Otherwise, you're going to take something factorial, and that's if you care about the order. The order is important. And other times you're counting the number of possibilities where order doesn't matter. So here, there's 4 fruits, and you get to choose 2 of them to eat. But I don't care in which order you choose them. I just want to know, like, what are all of the different combinations. Speaking of which, you might have heard of a combination lock. It should be called a permutation lock, because order matters. So the only reason why I mention this is not because I'm like like a tight-ass English speaker, although sometimes I can be. It's to warn you against confusing the two. if you think which one of these should I be doing, an n factorial or n choose k, if you think about it like a combination lock, then you'll choose the wrong one. A combination lock is not this one. A combination lock is this one, because order does matter. If the unlocking code is 1, 10, 15, then if you try 15, 10, 1, the lock's not going to open. All right, so I don't know. At least this was something that when I was learning probability, I remember some people getting confused with. So, fine. That's counting. Let's see. Okay, I want to cover just one more thing on probability. Well, first, let me ask. Any big questions or any questions about this counting stuff? Again, I'll cover it again in more detail next week, but this is the overview. Thank you, Brian, for typing. I appreciate that. Okay. Then I want to cover I want to go back to probability and here, independence. So I talked about independence, and actually let me move this stuff down. That's not going to be easy. Ugh, God, I'd like to keep it together. It's fine. Okay, I'll just put it down here. This is disjointness. Definition. Disjoint events. A and B from the same probability space are disjoint if they share no common elementary events. A, B, C. Oh my God. A and C are disjoint. A and B are not disjoint. B and C are not disjoint. Okay, so this is one way of understanding it, is if there's any overlap, right? So these are disjoint, these are not disjoint, okay? That's pictorially. Another example would be a die, 1, 2, 3, 4, 5, 6. Probability 1 equals 6. This is a fair die. And let's say E even is 2, 4, 6. E odd is 1, 3, 5. E multiple of 3, 3, 6. So here, well, let me ask. How about a faft? A fafta here?
Hi. Yeah. Yes.
Yeah. Hey, did I say your name right? I'm sorry, it's not used to it. A fafta here?
Yeah, you got it.
Oh, great. So which of these 3 events are disjoint?
Wait, sorry. Could you repeat that?
Which of these 3 events
Mm-hmm.
are disjoint?
Would it be let me see. The last one, the 3 and 6?
This is disjoint from what?
I guess because it's like related to the oh wait. Yeah,
Epsilon
it's not related to B.
It's not related to B. Which is B here? Let me say this. A, B, C, if you like that. This is separate than the picture that I drew. You're saying that this is disjoint from what?
Um
Okay. Do you know
yeah, I think with that
intersect?
one. Oh.
Empty set. This is the empty set. So A and B are disjoint if their intersection is empty.
So if would it be because since the third one, the one with the multiple of 3, it doesn't tie in like with I guess because it doesn't follow the like the prior sequences.
Let me do this a little differently. There. These are the 3 different ways that you can. These are the 3 combinations.
Mm-hmm.
Yeah, here we care about combinations. 3, choose 1. Whatever. So these are the 3 combinations of the ways that you can pair these events. What is the intersection of A and B?
I'm not sure.
Do they have any elements in common?
No.
No. So that's the empty set.
Okay.
Empty set. Okay. How about A and C? Do they share any elements in common?
Yeah, 6.
6. Right. Okay. And how about B and C?
Oh yeah, they do. They share the 3.
Share the 3. So, of these, which are the disjoint events?
The first one, the one with A and B.
Yeah, right. Yep. Yeah, these 2 are disjoint from each other. Very good. Thank you. So this is A intersect B equals the empty set. I.e. whatever. Okay. And just if you wanted to confirm that this is pictorially also true, if you have 1, 2, 3, 4, 5, 6, then actually I'm going to write this differently. 1, 3, 5, 2, 4, 6. E even, whatever, A is this. B would be this, so no intersection. And C is 3 and 6. So C overlaps A on this element, and C overlaps B at this element. So this is sort of a different pictorial thing. But they don't share any common elements, A and B. So they are disjoint. All right, let's take a break, but I will leave you with a question to think about. If A and B are disjoint, are they independent? So you can think about that during our break. Let's come back at 8:30. All right, welcome back, everyone. So before our break, we were talking about disjoint events. These are events that share no elementary events in common. You can view this pictorially by them not having any overlap, or as sets, insofar as do these sets, is the intersection between these sets the empty set or not? By the way, you can also write, if you so desire, you can write an empty set just like this, with the set notation and nothing inside of it. Whatever. So I asked a question. Are disjoint events independent? Anybody think that they have an answer?
They're actually dependent.
Okay, why are they dependent?
If one event happens that's disjoint from another, if it happens, we know that the other one cannot happen, so they are dependent.
Very, very good. Yes. In fact, it's the they're not just dependent. I mean, there's different gradients of dependency. Whatever. This is as dependent as you can get. Let's see. And your reasoning is perfect. Very good. Thank you so much. If A and B are disjoint, are they independent? This is something that lots of students confuse. They think that disjointness is independence, which is couldn't be further from the truth. Answer: no. If one event occurs, the other must not occur. So the probability of A given B is not equal to the probability of A. If B happens, then this on the right-hand side, this equals 0. Because if B happens, then you know that A doesn't. And this is assuming that A has a non-zero probability, then this is just the probability of A. And these two are not equal. Okay, very good. Right. So I want to get, I want to introduce probability distributions. Random variables, aka probability distribution. I'm going to be copying some of my older notes because I put time into them and I don't want to redo them all. Ooh, make that smaller though. Jeez. I want to keep everything on the same screen. That's for printing by PDF. Okay. All right. So here's the motivation behind random variables. Probability cares about events and their probability of occurrence. Again, a probability space is two things. It is a set of all possible outcomes along with the probability of their occurrence. You have to have both. Random variables assign numbers to events. This is why it's called a variable, because it's going to take some real number value. So here, this is a function, often called x. And like a probability function, this maps the set to a number. The reason why assigning numbers to events is useful is because you can compute averages, especially, but variance and other algebraic quantities that you can't do with probability. Random variables are also called probability distributions. I will go back and forth between the term random variable and the term probability distribution. Now, I want to emphasize that a random variable, or in a probability distribution, this is something that's built on top of a probability space. Okay, so what I mean by that is a random variable is made of three things. That's the set and the probability. So that's a probability space and a function x, where this is the function x. It maps things to the real numbers. But it's built on top of a probability space, or it extends a probability space. so this is why we need to talk about probability before we talk about random variables, because random variables are an extension of a probability space. With a random variable, and this probability here comes from the probability space. So, all right, now let me see if I can copy this. That'd be great. Okay, to emphasize the fact that a probability space does not deal with numbers, here is a cube. Okay, so I didn't want to use a die, because a die you could say 1, 2, 3, 4, 5, 6, but probability has no need for numbers, or if there are numbers, they're meaningless in terms of if you add them together, if you subtract them, like it doesn't make sense to do this inside of a probability space. It would be like in this cube saying what happens if you take yellow minus orange. Like it just doesn't really make sense. But you can extend this and answer those types of questions with random variables. So here, sorry, I guess I'm copying these over from other notes. The sizing is all wrong. All right. Let's make this a bit smaller as well. Great. So this is a probability space. Okay, here are the events, 1, 2, 3, 4, 5, 6 of them. And so this is the set, and this is the probability function. So this is the probability space. Now, how am I going to do this? Just a moment. You're going to not see the screen. I need to highlight something. To copy this. Great. Resize this. Great. So here is our probability space, all right, that describes this cube. And the random variable takes each of these events, takes every single elementary event, and maps it to a number. Again, mapping here means it's a function. And this is the function x. So all three of these taken together, this is a random variable. Okay, you have 1, a set, 2, a probability function, and 3, a function x. Okay, these three things make a random variable. And so here is a set of events, and the mapping are these arrows. And it maps things to some real number. No complex numbers, but real numbers. These include numbers like pi, like e. It includes irrational numbers, but whatever, real numbers. Nothing, no square root of -1s. And that's it. That's all that a random variable is comprised of. The probability of one of these numbers, again, a random variable is not a number. It has a probability of being a number. So this, for example, the probability of the random variable being the number 6 is the same as whatever the probability was that was assigned to this event. The event that it is mapping from. So here, the probability of 3, the number 3, would be the probability, I shouldn't say face 6. The probability of, that's like a light blue. Should be this. Whatever. Well, shoot. Whatever, this shouldn't be face 6. This should be a color. The probability of this number 3 is the color that maps to 3. So probably whatever this color is. Okay. Any questions? Everybody following so far? Please type yes or no. No questions, no questions. Very good. If you do have questions, please ask, because I hope that things feel kind of easy. But as you see with the example that we were working through earlier, sometimes when you're actually trying to do it, it gets it can feel complicated, or you might feel lost. I would like it if you don't have that. All right. So this is sort of the random variable. I'll call it the random variable perspective. I want to give a different perspective, which is why it's also called a probability distribution. From the probability distribution perspective, this is going to be a discrete probability. So here we have the number 1, 2, 3, 4, 5, or 6. Here you write this is x equal to x. So I write big X's this way and a little x this way. That way little x's don't get confused when I'm using a little x here, which is a multiplication. So this is big X, whatever. Oftentimes you'll ask about the probability that x equals, for example, 3. What this means is, for example here, the probability of x equal 3, actually I'll just write that, x equals 3, is the probability of the event that defines this value. And here, this is a probability. 1/6. And one thing to notice here, if you're drawing this type of, this is called a PDF, probability distribution function. Or a PDF. So a PDF has area 1. So the width of each of these blocks is equal to 1. And the height is whatever its probability is. So you can imagine taking like a block of clay or something that weighs 1 pound and cutting it up and distributing it somehow. But the area of this is equal to 1. Okay, that's an important thing for PDFs. There's also something called a PMF, which is a probability mass function. I won't talk about this today other than to say that PDFs look like this, like bar charts. PMFs look smooth. We'll talk about the smooth thing next week. For today, we're just talking about these bar chart looking things. So this is why this is from a perspective that gives the reason behind the naming of a probability distribution. Because you take something with an area of 1 and you distribute it such that each of these chunks are this is a fraction that equals the probability of it happening. Whichever way you think about it, really it's good to have both perspectives. Sometimes it's good to think about it more as a random variable. And a random variable, you can think of it like a black box with a screen and a button on top. And you push the button and you'll get some number. And you'll get this number with a certain probability. That's the way to think about it from the perspective of a random variable. It's a box, you push a button, and some number appears with some probability. From the distribution perspective, you're thinking about it more like a graph. Okay. So as I said before, the reason why we care about random variables is because you can do things like compute averages. Here, if I ask you what's the average of this cube, it doesn't really make much sense. You mean like the average of colors? Like, are you blending them together or something? Like, what if it's 2 songs? You know, what's the average of these songs? Or 2 sentences? What's the average of 2 sentences? You know, today's hot and I'm hungry. What's the average of that? These are sort of things without meaning. But you can talk about averages of numbers. This is called expectation. The expected value. expectation. And you can do lots of stuff with expectation. Knowing averages allows you to do a ton of really fancy, cool things. We'll talk about some of them in this class. I write expectation this way, an E with an extra line, whatever. And X here is the random variable, and this is defined as sigma X and X times the probability that X equals X. Okay, some notation notes. Notes on notation. So this small looking C, or like with a weird looking lowercase e or something, that just means that it's an element of a set. So, for example, 1 is an element of 1, 2, 3, 4. Sorry, my curly braces look too much like my 3s. Okay, so here, 1 is an element of 2, 3, and 4. Also, 2, 3 is an element of 1, 2, 3, 4. Okay. 5 is not an element of 1, 2, 3, 4. Okay, so if you put a slash through it, it means it's not an element in it. So that's this. Let me make this curly. So for all of the different values in X, this means sum. And example, the sum of I equals 1 to 3 of I is 1 plus 2 plus 3. So you start here, and you start with I equaling here, and then you iterate it 1 by 1 up until you reach this value, and then you stop. Here, you don't have any values on the top, because this is just taking elements from a set, not iterating through all of the numbers. Because maybe these numbers are different, right? I mean, if X is equal to, I don't know, pi, for example, then you wouldn't go pi plus 1, pi plus 2. It doesn't work like that. You just go each element in the set. And so then it's whatever the value of that element is times the probability that the random variable takes that value. So this is an average. I'll give one concrete example of above. Example, X from above. Then E of X. Give myself some more room. So E of X would equal 1 times the probability that X equals 1, plus 2 times the probability X equals 2, plus 3 times the probability x is 3 plus 4 times the probability x is 4 plus 5 times the probability x is 5 plus 6 times the probability x equals 6. Fine. Okay, and taking the same random variable, so x from above, that's this x here. This is 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6. Just finish this up. And so this is equal to 3.5. Okay. So there's a couple things that I want to say here. First of all, if you get stuck on this notation or something, please let me know. I don't want to talk down to anybody, but at the same time, you know, I don't know if you know what certain symbols mean and stuff, so I'm just trying to cover my bases. For this thing, now we can talk about like a die. Okay, a die with 1, 2, 3, 4, 5, 6 on it. What does it mean for the expected value to be 3.5? Let me ask a question. Who have I not spoken to today? Yuhi.
Yes.
Hey, so what do you think it means? Like if you have a die and the expected value of it is 3.5, will you ever see a 3.5 if you roll one die?
No.
So why would that be the expected value of it?
I guess maybe the average of the possible outcome. I don't know. It's not the actual average, but it's the average of its possibility.
Yeah, great. Yeah, I think the first way you phrased it is fine too. Yeah, it's sort of the average value that you would get from it. So, yeah, this is sort of, if you were to roll a die once, you'll get some number, and then you roll it again and you get another number. What's the average of those two numbers? And then you roll the die a third time, and now you add up all three of those and divide by 3. You know, it's the average of those 3 numbers. And then the average of the 4 numbers if you roll it 4 times, and on and on and on. You would get, if you do this 1,000 times, you would get a number that's very close to 3.5. That's what it means. So now I'm sort of arguing from a bit more of a frequentist position. You do a trial or an experiment some very, 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 very large number of times, and then you take the average among all of those experiments. But it's a good thing to remember that the expected value does not mean that that is a number that you would see on a single trial. It's the average of what you would see over many, many, many trials. Okay? Another thing about the expected value is that it's a number. It's always going to be just some number. A random variable is not a number. A random variable can be a number with a certain probability. The expected value, though, is a number. All right, so that's another important distinction to keep in your head, that a random variable is not a number. It has a probability of being a number. Why does it have a probability of being a number? Because it's built on top of a probability space. And a probability space has a probability function. So, and a random value adopts the probability function from some probability space, as in here. This whole thing is the random variable, including this probability function. So you can never talk about a random variable being a number. You can talk about the probability of it being a number. Unlike the expected value. The expected value is a number. You can calculate it. Another way to think about the expected value that works is from sort of a physics perspective, which when I was talking about this thing from the probability distribution view now, that you have this thing that weighs like 1 pound, and then you're divvying it up, this 1 pound thing, proportionately according to the fraction that lies on top of a number is its frequency or its probability. Now, if you do this with like a physical thing, then where is the center of mass? Here, it would be here, 3.5. Right? If you if this was a big plate with 6 things on it, if you put your finger right at 3.5, then things would be perfectly balanced on the left and the right. And that will always hold true for the expected value. Even if you have very strange looking probability functions, like if you have a big mass here and a little mass here, well, then, the expected value is going to be somewhere around here. You can just sort of imagine where you would hold it such that it wouldn't fall over. That is completely consistent with the mathematics behind expected value. All right. Yeah, so there's a question on your homework that I want to, it's, oh, sorry. There's a question on your homework that asks you to show that for random variables x and y, show that the expected value of x plus y is equal to the expected value of x plus the expected value of y. So this is a property of expectation. In fact, this is called linearity of expectation. So I'm not going to prove this because I want you to try this on your homework. But this is a very nice property of expectation. You can have two different random variables, and if you want to know the average of them being added together, then you can just find the averages of each by themselves and add those together. And this is always true. This is true if x and y are independent, which is when things are easy. But what's really cool is it's true even if x and y are dependent. So even when you have really complicated stuff like dependencies that just make things a nightmare, trying to figure out, how this thing affects that thing, and it can be bad. If you work with the expected value of stuff, everything is a nice and easy world. You can just take each thing by itself, figure out what its average is, and add up the averages. Very, very nice. So this is a very useful property of averages. And just to emphasize, I don't know, maybe you guys already know, but why dependent events are so hard to work with. There's something called the three-body problem. Which, by the way, there's a sci-fi trilogy called the Three-Body Problem, which is excellent. If you like sci-fi, holy cow, it's fantastic. Anyway, the two-body problem is, let's say here you have Earth and here you have the sun. How is the Earth going to move around the sun? Well, the Earth has gravity, and so the Earth is kind of, or the sun is kind of being pulled toward the Earth, and the Earth is also being pulled towards the sun. And you can figure this out. It's pretty simple, basic physics. How do two bodies gravitationally influence each other? And I pretty much just drew it here. I mean, A pulls on B, and B pulls on A. So this is B is being drawn to A is being drawn to B, and you can figure out what the gravitational pull is between them. The three-body problem is when you add something C. And the reason now this is, it gets super complicated and there's no answer for it, or nobody's been able to calculate this until today. I mean, this is an open problem. People don't know if it's even something you can calculate. Two bodies, super simple. You add just one more, it's a three-body problem. Why is it complicated? Well, A pulls on B, and B pulls on A. C is being drawn towards B, and B is also being drawn towards C. But now now that B is being pulled towards C, that changes how B is being pulled towards A, because B is also being pulled towards C. At the same time, C is also being pulled by A, and A is being pulled on by C, and so, all of these things are dependent on each other. Once C pulls B, that changes the calculation on how B is pulling on A and how A is pulling on B, and it just becomes a nightmare. So that's a succinct example that I can think of about why dependent events can just kind of be a nightmare. Independent events are much easier to work with. Great. What would you guys rather? We could either take a break now and end closer to 10, or we could just blow through it and just sort of finish class early. I have maybe another, I don't know, 20, 25 minutes before I'm done. All right, happy to do that. Sure. All right. Oh. Let me redo this. So there's actually one more thing about the linearity of expectation. One is that this equals c times e of x. C is a real number, or c is a scalar. Whatever, c is a number. If you take a random variable and you multiply it by a number, then the expected value of that is you just find the expected value by itself, and then later you can scale it by the number. Same thing. Similarly, and this is what I just wrote before, and what I want you to try to show in your homework, is that e of x plus y is equal to e of x plus e of y. Note, this is always true, even that's a very nice property, so I'm going to really emphasize it. Right. Okay, so first of all, I would like to know if there's any volunteers, otherwise I'll just pick out somebody, to try to work through showing why this is true. It's pretty easy to show. Okay, I haven't talked to Daria today, so how about you?
You actually have, but
Oh, okay, I'm sorry. Well, sorry. Well, let's stick with it anyway. Okay. How would you think about trying to go about showing this? You could show it by example, if you like.
I'm not sure. I was actually a little confused with this.
Ah, okay. Which part? This part? Everything expectation?
Yeah, kind
Yeah.
of.
Okay, good. It's fine. It's fine to be confused, but yeah, please let me know, because when we move on, you're gonna have a worse time. I'm okay with slowing things down. Yeah. How about the idea of a random variable? Are you okay with that?
I think so.
Okay. How about probability spaces? Do you feel okay with that now?
Yeah.
Yeah? Okay. So, Yeah, it takes a little bit of thought. Honestly, the first time I started learning about random variables, I found them very confusing. I think unnecessarily so. They're actually a lot simpler than I was making them out to be. So practice is helpful, and examples. So we'll stick to well, Daria, what do you prefer? Would you like to go through an example with a die, or go through an example with a game with like where you can win or lose money?
In the game, is win or lose like the only option?
Yes. Yeah. Yeah.
Then I go with the game.
Okay, great. So we'll do a simple game. We'll make it as simple as we can. What can you invent a game that you like?
I'm not sure if I have the brain capacity to do that right now.
Okay. How about we make a bet if it's yeah, like we can make a pretend bet together. What do you want to bet on?
If it's gonna rain tomorrow.
Excellent. Okay. So example. Bet if it's going to rain tomorrow. And do you want to say it's going to rain or it's not going to rain?
Not.
Not. Okay. So you win if it's not going to rain. And how much money do you want to earn if you win the bet?
$20.
$20. Perfect. All right. You win $20 if it's not going to rain, and 0 otherwise. Wait, do you want to? Do you just want to lose no money, or do you want to? I'll say no. You pay me. You pay me. And minus $10 otherwise. By the way, this is a bad bet because if you guys don't know, there's a hurricane that's headed our way. It's definitely going to rain tomorrow. So, okay. Anyway, great. So let's do a quick probability space. We'll build that first. What is the set that we're dealing with?
Rain or no rain.
Great. And now you can come up with whatever probabilities you want. I don't care. What's the probability of rain?
30%.
30%. Okay. I'll leave out the probability of no rain because it's 0.7%. I'm hoping people are okay with that. All right. And so x is going to be a function that maps rain to $20 and no rain to minus $10. Okay, so these are real numbers. So far, this is a perfect random variable. We have a set of events, we have a probability function, and we have assigning events to numbers. Okay. So the expected value is if we played this game every day for this whole year, then would you expect to earn money or lose money? Should you play this game? That's an important thing to ask yourself if you're making bets. is the game worth playing? If you play it a lot, are you going to, on average, win money, or are you on average going to lose money? So that's what we're going to try to calculate with the expected value. If it's some positive number, you should try to play this game with me every day. If it's some negative number, then I will be taking money from you over time. If it's 0, that's called a fair game. And sometimes you win, sometimes you lose. It's just a game you play.
Sorry,
Okay.
I just have a quick question. Why is rain $20 and no rain -10 and not the other way around?
Oh, I'm sorry. You're right. I'm sorry. Rain. You're correct. Thank you. Okay. So the expected value is going to be your average winnings. So this is going to be the either well, how would you think about calculating the average of your winnings?
Well, like, wouldn't you just add all of them like together and then divide by how many there were?
Yes, that would be an exhaustive way to do it. But then you actually have to play each time. Or you have to run a bunch of simulations and then add them together. But we can save time by imagining it differently. Okay, let's say this. Sometimes you'll win, and then you'll get $20, right? Sometimes you'll lose, and you'll get minus $10, or you'll lose $10. Okay. Now, if you play this game 1 billion times, how often will you get paid $20? What percentage of the time?
It would still be the same percentage, wouldn't it be? Like 70%?
70%. Very good. Yeah, that's right. It is 70%. So 70% of the time you'll win, and therefore how often will you lose?
30%.
30%. So this is exactly what you're saying. I mean, this is an average. Oh, sorry. Yeah, you play the game many times, and then you take the average. Well, you can. This is sort of the ideal way of doing that. How to say? Okay, what you could do is if you actually played it, maybe it's 20, 20, minus 10, 20, minus 10, minus 10, minus 10, right? And you can play this game many times, right? Now we've played it 1, 2, 3, 4, 5, 6, 7, 8 times. Let's make it 10 times just to make the numbers easier. Okay, so here, if you want to calculate your average winnings, then you say you add all these together and then divide by the number of times you played, right? But this is the same as taking the number of times, or the number of times you win, which is 1, 2, 3 out of 10, plus the times you lose, which is 7 out of 10, right? I mean, this on top and this on, let's say this and this are the same, right? I'm just grouping all of the minus 10s together, and I'm grouping all of the 20s together. Do you follow?
Yeah.
Yeah. So if you play this game now, maybe you happen to win one more time, then you lost. So this would be your empirical average. So this is what it would be if you played it just 10 times, and maybe you got lucky this time, because you won one more time than you normally would. But if you play this game to infinity, you expect this number to approach the probability, and you expect this number to likewise approach its probability. And so that's exactly what this expectation is. This is how much you win and the probability of you winning, and this is how much you lose and the probability of losing. Does that make this equation make a little bit more sense, or are you still a little uncomfortable about it?
Oh no, I get it. So we just always assume that it's going towards infinity.
Yes. Yep. Mm-hmm. Yep. That's a valid way to think about it. Mm-hmm. Oh, okay, and whatever this equals $11. So you expect over time to win $11 each time on average. So you should definitely play this game often as you can. Thank you. Dari, if that makes sense to you and you're happy with it, I'm happy.
Yeah, good. Thank you.
Yep, sure. So let me pick out Jenny. How about you?
Yeah, I'm here.
Okay, good. So what I want to prove, and then we're done with class, is just this one. E of cx equals c of ex. So what this means is that you can scale the payouts first and then compute the expectation, or you can compute the expectation and then scale. Are you happy with this example?
Yeah, I'm fine with it.
Okay. So let's take we're going to multiply we're going to make the game quote unquote more interesting by playing with more money. Do you want to pay, by how much more money do you want to pay? Twice as much, 10 times as much, 1.5 times as much?
Twice as much is fine.
Twice as much? Okay, good. So then now we double the bets. So that means that we're going to make c equal to 2. So cx is now going to be minus 20, and this is going to be 40. Okay? So how does this change?
Would it just change the 20 to 40 and then the negative $10 to negative 20?
Okay. And what does that equal? Can you tell, or?
I got 20. I got 20.
20? Hold on. Doesn't sound quite right. You want to double check? You're close, but not quite right. I'll tell you, it's 22.
Okay, yeah, I just got that. I think I typed something in the calculator differently.
Sure. Okay. Yeah. So here we just calculated it. Oh, this is E of CX. So this is first multiplying the payouts and then calculating the expectation. But as you might notice, this is equal to C times E of X, which is 2 times $11. A really quick visual way to look at this is here. This is minus 10. Here is 20. And so in the middle is 11. Oh, and this has a probability of 0.7 and 0.3 here. So 11 here is sort of the midpoint between these. This number counts for more. That's why it's 11. It's not exactly in the middle, but because this number is sort of heavier, I guess. So if I'll do it this way. If we were to multiply it by 10, then everything gets multiplied by 10. Right? If I multiply these by 10, well then the middle point isn't going to change, except for the fact that it has to scale the same way. So this is another way of thinking about why this fact is true. Okay, so that is it for today's class. Oh wait, are random variables just assigning numbers to things that can be quantitatively defined? It is assigning numbers to things that can be quantitatively defined. Quantitatively in the sense of what? Can you unmute yourself real quick? Raymond?
I think I did a typo there. I meant to say can't.
Oh, things that can't be what do you mean by quantitatively defined?
Well, like before you use an example like colors,
Yes.
like trying to find an average color, like there's no such thing. So like you just assign numbers to each color. Is that what it is?
Yeah, it's all that it is it's a simple extension to probability spaces, where instead of where you assign numbers to events, and therefore the probability of those numbers is equal to the probability of those events. You could have a probability space where the set is of numbers, but the thing is that those numbers don't have any meaning. In the same way that you could have a set of sentences, or a set of albums, or a set of movies, or a set of shapes. A set can be anything you want in a probability space, including numbers, but if you're using numbers, they don't have the meaning of numbers. They're just symbols that you like. So, but random variables allow you to assign numbers to any of these things inside of your set. And then those numbers have number means, where you can do things like this, compute averages.
Okay.
Yeah.
All right, cool. Thank you.
Yeah, thank you guys. Some of this stuff, I really think it just takes a little bit of thinking about, coming up with toy examples and stuff like that. If you have questions, I'm always open for them. I will sign the homework after class, and I'm going to try to make it due next Tuesday at 11:59 p.m. So it's short, just 3 questions, and good luck. Thanks, everybody.